So Stefan Edelkamp's the last speaker, and he's going to be talking about Connect 4.
Yes, I would like to talk about genetic algorithms, but that's what I'm not doing. This is a talk without any heuristic. So you can be happy, there is no heuristic inside. And although this looks like problem dependent, I'm really more interested in the combination of symbolic and explicit, because both seem to be quite well doing in the planning community, and there is some reason of doing things together. Okay, some of you may be familiar with development that is in the search community. They do what they call BitVector Search. The idea is not to represent the state as a vector of entries, but to represent the state as a memory address in a huge, huge bit vector. And you have a perfect hash function that maps the state to the index, and then you only need bits to say visited, not visited, and you have to have efficient function for transforming the memory address to the state and back. And this works well in permutation games. Here you see the bit vector. So this one is a state, it makes babies, and you will see they will be here. And you go along that bit vector by scanning the bit vector. You can do breadth-first search with that. Well, there's no heuristic, so you would not do A star. Okay, here in permutation games like the 15 puzzle, you can explicitly work on that function. We call it rank and unranking. There are functions that are efficient to map a 15 puzzle state to an index and vice versa. So if you would do it, so it's between 0 and n factorial. And you have to be careful with the blank. There are other games, I'm not going into it, where you can devise those rank and unrank function directly, like in the PAX Solitaire or in checkers or so. It does work with more than one color, so it's an n over k problem, but you can devise the function. It's more complicated, but it's fast enough to be evaluated, and we won't go into this, but there are specialized functions for specialized problems. But here we are in planning, so we want to save memory, so memory is the core problem, not time. Memory is the core problem, and let's see whether we can apply the technique also to more general settings. And here we have another memory saving technique, which is BDDs. And as Paolo is here, he may have introduced that to planning. And here you see the effect. If you have states and BDD nodes, then sometimes you save orders of magnitude. Here it's not that much. But the idea is just that one pass to one thing is a satisfying assignment and corresponds to one planning state. And if you have sets of planning states and you have to think of sets instead of singletons, then you can actually use this to represent a set of planning states better than just the enumeration of the state itself. Even the enumeration of bits is sometimes not better. Okay. And here you have my research goal, which I followed. I wanted to strongly solve the Connect 4 problem. It is already solved, so it's boring. Everybody knows that you have to put the first one in the middle. But for me, it's important to strongly solve it, which means I have a mapping from states to actions. A full mapping. It's large. Well, these are lots of states. But the full mapping from states to action. And can we compute that? And can we store that? And this is the idea, and it's important for synthesizing controllers. When you really want to have a controller synthesized, game is then just the environment against the robot. And so how can we do it? So what is known as retrograde analysis, you can actually go backward and forward, generating the state space, and then classify the states from what you have seen. So and at the end, you will be back into the start state or in all states, and you know their game theoretical value. Here we use BDDs because that's important for this Connect 4 thing. You can generate the entire state space in 4 or 5 hours. And if you do it explicitly, you need months. So there's a difference between the two. And what you have is that you have on disk, these are getting bigger and bigger, you have on disk the BDDs. And then what we need is a mapping from the BDD to the bit vector. So we want a perfect hash function based on the state reach on the state set that is in the BDD. And this can actually be done. So, okay. So what we want is a rank and unrank function for this connect 4, and it's not as easy as it was in the sliding tile puzzle or in the other permutation, this PEG solitaire. Here we have lots of intermediate goal states, which make things more problematic, and if we want a minimum perfect hash function, so this is a bijection, then you won't find it by just designing it. So how does it go? So the algorithm was already, the rank and unrank was already there for a while. We use it also to sample randomized assignments in a BDD. And here you see a BDD. And you will see that when you somehow look at the lexicographic ordering on the assignments, then the first 3 will end up here, the other ones here, here one. So you have 8 satisfying assignments, and they somehow belong to some partial parts in the BDD. So what is done is you have to pre-process your BDD, which is there, and attach what is called SAT count values to the BDD nodes. This is not a difficult operation. Bryant, in his first paper on BDD, well, he was not the inventor of BDD, as is often cited. That was Akers or some other people. But he at least get efficient algorithm also for the SAT count. So you do not have to count all the things, but you go backwards. So there's one satisfying assignment here, one is here, and then you add up the values from here to here, and if there are some nodes left, you have to multiply it with 2 to the something of missing variables. And you can then do it in linear scan on the BDD. And then you attach that to the node. We have done that in CUT. So CUT is the BDD package. It has some canvas, but we will go to it. So now that we have the SAT count values, we can actually do this rank and unranking. And this is somehow linked on the 0 links. So as shown in the previous figure, if we add up the values of the non-taken 0 links, then we have the unique representation of a number in the lexicographic ordering. And this then allows us to do the trick. So we go backwards and do now want to classify a state. So we look in the bit vector. So we have this mapping, and then we ask whether state is 1 or not, and then we return the player's cost, or if we are in the last layer, then we could either see that it's a draw or win or loss. So if it's a draw, then we are it's okay. Otherwise, we make children, and the children in the next layer are checked for their classification value. So it's somehow you make babies, so you unrank, make babies, and then rank again. And for the ranking, you look for the values, and if all successors are lost, you are lost, and so on, as it is usually in the rhetoric analysis. There we have different options. One is to determine a goal by just a procedure, but you can also determine the goal by what you have computed by the goal predicate, which is actually a GDL input that we take for the GDL as a game description language used in the general game playing competition. So we try to be as general as possible, even though it is, of course, looking as we do only Connect 4, but we want a strong case. And so these two things are problem independent, but this one is problem dependent. So either you look in the layer of the goal state, or you make the babies and look there if the successor is there to know whether it's a goal or not. We want it to be fast, and if you have a long bit vector, then you probably are better off with having several threads. So you cut your bit vector in some pieces and give that to thread 1, that to thread 2, that to thread 3. And this one is, because it's on the CPU, you can actually access the successes concurrently. It's a concurrent read only. Okay, that is multi-threading, and the problem is with memory. So I'm more or less only concerned with memory, because memory will get time when memory is lost. Then it will thrash your computer. But cut, we could not do this. So for the BDD, we could not get concurrent access easily. So in some cases, you will see it, if we have more threads, then we have several instances of cut. So this costs us a bit, but because the BDD are smallish, it's not as bad. So you will see it here on the time we have, and we are interested in the memory peak. I think it's 6 times 5, so it's a smaller one. But still, you see, there is a speed up in doing parallelism. But because of the cut problem, we have some increase in space. Usually it shouldn't be that big. But still, if you would do it explicitly, then you would probably need more space. These are the different goal evaluations. And you see there is a decent speed up. Well, I only have 4, of course. So it might be better if you have more. So the 6 times 6 we could solve. And it took us a while. We had a personal computer on my desk with 24 gigs, and it finished in about 11 days. It was quite okay in generating states per second. So first we have generated the BDDs in a forward search and then classified with the bit vectors in backward search. And the result was already known. So the second player wins. The 7 times 6 was the motivation, because I want to solve this, and that was actually on a 192 gigabit machine that Peter ran it in Saarbrücken, and he got forward in the BDD search, and you can also classify with BDD. But here's a break. So here's out of memory, even within symbolic search. He already passed, as you may see, he already passed the peak of states, but the peak of BDDs is a little bit different to the peak of so he had already classified 3/4 of the state space, but the rest we still need, and he can't do it with BDD. So the idea was to get there with bit vectors, and that's probably the bad news of the talk, is that we haven't done it. We estimate how much it would take, so probably a 2-bit state, like one loss or draw, would take 80 gigabytes, so it may be sufficient if we need 2 layers, and we probably fit this and the BDD into this 192 gigabyte machine. So we were quite okay, but then we estimated the running time to be like months. And the big machine we only had for some initial experiments. This is hard work, but it's at least the real one problem where on current machine the problem really arises. Okay, yes, but I'm already done. So, but I will discuss a bit more, because what I think is the Connect 4 is not what is really interesting. That is actually that we have a bridge between symbolic and explicit state search. That you do symbolic here and explicit there. And what do you need for that? So in a usually planning problem where you only search a path, it does not make sense to generate the entire state space with a BDD. Then you have solved the problem already. So you need a more harder task. In this case, it was classifying, so game playing. It can be model checking, where you search for loops. You can't also not do it in one sweep of the state space. Or in Markov decision processes, it's also that you have the state space and then you iterate with value iteration over it. So you can use a BDD to compress the state space to only a few bits. And the case was chosen because the memory problems were real. The input was general, I already said. Some goal predicates, I already said, are problem dependent, and some are domain independent. So this is, it is a domain independent technique, and therefore may belong to this conference. So otherwise I would. Okay. The other thing is there is a bunch of research work that also, if you have a terabyte file on your disk and you want to compress it to get it in main memory, then there is an option which is called minimum perfect hash function. You can download it from South America somewhere. And it actually compresses you. It's a memory-based perfect hash function, but the memory needed is just 2 bits per state. So this is so you can actually do your state space generate on disk, and you can, for doing MDP or other things, you can compress it to 2-bit and do the bit state trick. You can do it explicitly, but what the talk was about, you can do it also symbolically. So we have actually the symbolic equivalent of this line of work, which is sometimes coined to the term semi-external search. And this I already have said, but not implemented, so there's lots of things to do. Thank you.
Okay, so we've got time for questions. Anyone? I have one. So you mentioned you can split up the bit vector across CPUs. You mentioned you can split up the bit vector so you can use multiple threads.
Yes.
So, does the hash function give you any sort of locality guarantees that when you make babies, they're going to be close in the bit vector to the state they came from?
Yes, well, this is really a question we worked so hard at, but not in the context of this problem. But it is true, if you have 24 gigs and you have a hash function which is 24 gigs, a hash table, then you get to locality problem, because some is somewhere in that bank of the RAM, some is somehow in that bank, and you do not achieve decent speedup because all these things have to bubble up in the cache hierarchy. So there is locality problems with hashing. So, and then comes the you want to have local hash function. It's also if you have SSDs as a secondary thing. So these are quite okay with random access to data. And then you actually need some hash function. Hash function should distribute. But here you want to have them locally. So you need to work harder on real new algorithm to have some form of locality, but also some form of distributedness. And well, this is at least this forward-backward hash computation is something that I think from a theoretical point of view will be very important in future.
We did have similar problem when we randomized the same PDB compared to maximization. The evaluation time went down quite a bit. On maximization, but on randomization, it didn't. The same PDB, and the reason was exactly the same thing. It had to keep going all over the place, so it wasn't able to cache the actual most likely results. So it was a locality problem all over the place as soon as it started moving around.
Okay, I think we're done. Let's thank Stefan again.